Welcome to homework.
In this problem, we are given the two half reactions that take place in a galvanic cell, and we are also given different conditions for the concentrations of the aqueous species, and we want to predict whether the cell potential at non-standard conditions would be greater than or less than the cell potential at standard conditions. This means that we need to use the Nernst equation shown here in order to compare the cell potential at standard and non-standard conditions. So one of the components of the Nernst equation is reaction quotient Q. We are given information about the species concentrations in parts A and B of this problem, and that will allow us to determine the value of Q. And then the Nernst equation, along with that value of Q, will help us to determine whether E at non-standard conditions will be greater than or smaller than E at standard conditions. So these are the two half reactions that we are given, and we can look up the values of their standard reduction potentials in the table. And we know that since this is a galvanic cell, that the overall cell potential has to be positive. So therefore, we flip the reaction that has a smaller value for its standard reduction potential, and that would be the first half reaction involving silver, since 0.80 is less than 1.78. So we take that bottom half reaction and we keep it as it is, and we reverse that top reaction, and we see that we need to multiply that top half reaction by 2 to cancel out 2 electrons on either side. And when we do that, we get the overall equation taking place in this galvanic cell. And now, based on this equation, we can write out the reaction quotient Q. We know that the reaction quotient only involves aqueous species, and therefore solid and liquid species are not involved. In the numerator of the reaction quotient, we examine the products of the overall equation. For the products, we have liquid water, and since that is not aqueous, we cannot have it in concentration units, so we do not include it. We have aqueous Ag plus with a coefficient of 2, so we take the concentration of Ag plus and square it. For the denominator of the reaction quotient, we look at the reactants. We have solid silver, so that does not factor into the reaction quotient. We have aqueous hydrogen peroxide and H plus ions. So we take the concentrations of each one of those, and for the H plus, it has a stoichiometric coefficient of 2, so we square it. So now we can calculate out what the reaction quotient would be based on the conditions in part A. We are told that the concentration of Ag plus in part A is 1 molar. So we square that and divide it by the concentration of H2O2, which is 2 molar, times the concentration of H plus, which is 2 molar, and we square that. And that comes out to 1/8. And now, based on the Nernst equation, the cell potential at non-standard conditions is equal to the cell potential at standard conditions minus 0.0591 over n. And we know from this equation that n is 2, since we had to multiply by 2 on the bottom half reaction to get 2 electrons to cancel. We have 2 moles of electrons times the log of Q, which is 1/8. And so when we calculate that out, we see that E is equal to E at standard conditions minus negative 0.027. So therefore, since we are subtracting a negative number, we are actually adding. So to get from E at standard conditions to E at non-standard conditions, we have to add a non-zero value, and that means that E at non-standard conditions must be greater than E at standard conditions. Now for part B, we are given different concentrations to plug into a reaction quotient expression Q. We have, for the concentration of Ag plus, 2 molar this time, and we square it. And now we divide this by the concentration of H2O2, which is 1 molar, times the concentration of H plus, which is 1 times 10 to the negative 7th molar, and we square that term, and that comes out to a reaction quotient Q of 4 times 10 to the 14th. And now we use a Nernst equation again to determine how E at standard and non-standard conditions compare. So E is equal to E at standard conditions minus 0.0591 over 2 moles of electrons again, times the log of Q, which is 4 times 10 to the 14th. And so now E is equal to E at standard conditions minus, this time that comes out to be a positive value of 0.431. So to get from E at standard conditions to E at non-standard conditions, we had to subtract a positive value. And if that's the case, it must mean that E at non-standard conditions is less than E at standard conditions.